In this third segment of this screencast, we're going to talk about the next major separation principle, which is separating between parts and the whole. Separation between parts and the whole is it's different from both separation in time and separation in space, because here we're talking about a situation where at the same moment in time and in the same space, a group of components or elements in a system can have collectively one property at what we'll call the macro level, while individually a different property, even a conflicting property, at what we'll call the micro level. So when we consider these separately, or we conceptually separate between parts and the whole, we can do one of two things. We can hide or minimize one of these properties, or we can express them both at the same time and in the same space, but at different scales. If neither of those two things will help us, then we move on to the next major separation principle, which is separation by direction. But if either or both of those things would help us, then we go through these various categories of separating between parts and the whole in search of a solution. So same kind of high-level algorithmic approach as we talked about with separation in time and separation in space. You first assess whether that general type of separation principle is likely to be useful for you before you decide whether to spend time on it or move on to the next one. I should also mention here that some authors and commentators actually refer to this principle as separation by scale. But these authors take a different approach to it, and that's why they use this terminology. And, there are others who use similar terminology, but you should just be aware that there are some who consider this to be separation by scale. So an example they start us off with here is a traffic light. The traffic light, there's a contradiction between the fact that it must eventually fail because bulbs burn out eventually, and especially with the kind of vibration that that kind of filament will receive. No matter how durable you make it, it will eventually fail. On the other hand, we want it not to fail in order to not cause traffic delays or worse. Now, I just want to point something out about this contradiction. Notice that the contradiction is between the fact that it must fail because of the inherent nature of a component and the fact that we don't want it to fail for safety and efficacy reasons. The authors use the term an output contradiction here because it's not like we want it to fail and not fail. In those cases, we're trying to reconcile a conflict between two things we want. In this case, we're trying to reconcile a conflict between something that we want, which is for it not to fail, and something that is inherent or unavoidable, which is the fact that it will fail. So that's fundamentally different than, say, the lap pool situation from the previous segment, where we want the pool to be large so that the swimmer doesn't have to do as many turns, and we want the pool to be small so that it doesn't take up as much space. Those are both things we want. But here, we don't want it to fail. We just accept that it will, and then we make that part of the contradiction. So they also use the term implicit contradiction for that. So let's briefly go through the little algorithm and see if in this situation separation between parts and the whole would be useful. So at a critical moment in time, should either its failed state or its not failed state be hidden or minimized to help solve the problem? In this case, yes. If the bulb failure were minimized after the point of failure, that would definitely help to solve the problem. Now, the second alternative doesn't really apply here, but since it only takes one or two, we know that we should stick around in separation between parts and the whole to try to find a solution. In this case, I think that we will see some principles within this overall separation principle that would help us to solve that problem. In formation, we're combining multiple elements that each have one desirable property, but together they have another desirable property. Now, the interesting thing about formation is that they don't interact, because if the parts interact with each other, then it becomes merging, which we'll talk about in a moment. So in formation, we're talking about just the accumulative effect without interaction between the components. So the example they give here is a series of small, carefully arranged simultaneous explosions calculated to have an aggregate desired effect. This is, we talked about this example also in the principle of separate gradually. In that case, the explosions weren't necessarily simultaneous, but in this case, they could certainly be. And funnily enough, I think this first example of formation also gives us a potential solution to this initial example of the traffic light situation, because individually a small fraction of a light bulb that could comprise a fraction of the overall bulb size we're looking for would give us the advantage of not mattering much if it fails, because it's just one small part of the overall light, but it gives us the disadvantage of not being enough light all by itself. So if each of the three main traffic lights, red, yellow, and green, is actually a collection of many smaller lights, then we have the benefit of having the constituent lights fail in just a little bit at a time. So moving on to merging, where the components do interact. In this case, we're thinking about the example of a car chain that you might wrap around your tires if the roads are icy to get better traction. So it's sort of an anti-slip device, if you will. You want it to be stiff in order to dig into the ice, but it needs to be flexible in order to wrap around the tire. In this case, there is an interlinking or an interlocking between the links, and this is essential in order to make the overall system, the chain, flexible. Yet each component of that chain remains as rigid as it ever was. So, by the way, this would be an example of when we were up here and we said we were looking for either this or this to be true. So the traffic light, we said, was an example where this first prong was true, but the second one wasn't. Well, the chain link example is the other way around. There is a particular point in time, namely when you're driving the car with the chain on your tires, that you want it to be both flexible so as to go around the tire, and not flexible so as to have each link dig into the ice. And you want those to exist at the same time, but at different scales. So as a whole, you always want the chain to be flexible, but link by link, you want each member to be rigid. So this is a case where it's this second prong that is the reason why we're separating between parts and the whole, as opposed to the traffic light where it was this first prong. So let's go back. Okay, the next one is carrier. So in the context of separating between parts and the whole, a good example of a carrier is sandpaper. In this case, we're dealing with the fact that we need a flexible material to grab onto and to conform around whatever wooden object it is that we're sanding, but the individual components on the other side of that sandpaper need to be rigid and inflexible so as to actually be sufficiently abrasive and rigid as to cut the wood as needed for the sanding process. So in this case, the paper serves as a carrier for all those small, rigid, inflexible pieces. Another basic example of a carrier is a capsule, where you put a powder that tastes really badly for medicine in a capsule, which typically gelatin, which is easily swallowed and more rigid and easily handleable, and this allows the drug product to have a different property at the macro scale versus at the micro scale. The next category here is called hiding part. This is when we have multiple elements and each element already has both of the conflicting properties separated in space. And one of these conflicting properties is undesirable. So we look for a way to hide only the undesirable feature of each element. The example they give for this is sharp edges of a can. It has smooth parts, it has sharp parts, and if you roll up the edges, then you conceal the sharp parts and protect them behind the smooth parts. I think an easier example of this to imagine is when you take a piece of Scotch tape and you turn it into double-sided tape by rolling it, or rather I should say rolling a piece of it around backwards and then taping it to the back side of the other end and then pulling it taut so that it's like you have a strip of double-sided tape. It's a common trick. And what that's essentially doing is hiding the non-sticky part of the tape on the inside so that only the sticky part is exposed all over so that you can have your double-sided tape in effect. Next, with countering, we're looking to cancel out an effect. Even if it means we have to have two properties that are undesirable in opposite ways, we just want the net effect for the overall system to be canceled out so that we don't have the undesirable property. One example of this, they give the example of a camera stabilizer. That's a common principle. Another example could be active cooling. So if you have a device that a part of it tends to get overheated, you could try to minimize the heat. You could try to do passive cooling. You could try to do just sort of convective cooling with a fan, or you could do what's considered active cooling, where you actually put something in there that gets cold, such as a Peltier device, right up against the part that's getting too hot, and coordinate them so that the net effect of the overall system is acceptable, even if there are parts that would be, all else being equal, parts that would be too cold and parts that would be too hot. The next concept is complementary directions. If I'm not mistaken, that's the spelling of complementary that has a different meaning from what I think they intend here, but that's okay. So with complementary directions, we're dealing with a situation where an object has the desired property, but only in one direction, and therefore they can be combined with similar properties oriented in other directions to have the net effect of a multidimensional property. So a good example of this is side airbags being used in conjunction with front airbags because they all constrain in only one direction. And so when you combine them together, you get the benefit of being constrained in all directions. Now, coordinated parts is when we have two different parts that provide opposite qualities, and they sort of average out or cancel out to provide the desired property. Now, this is different from a compromise because this is when the net effect of the coordination of these two opposing properties actually gets us to where we want to go. So the example for this is a water faucet. If you imagine a typical water faucet, you can turn it all the way on, but you can still slide it over to cold or hot or various places in between without changing the total amount of flow. And so if you have a desired temperature, you can get there with the proper balance of hot and cold water, and you can change that temperature by changing that balance without affecting the overall net volume of flow coming out. Now, this overlaps a lot with countering. I even gave an example of temperature control for countering where we have active cooling to cancel out heat to get to the desired temperature that we're targeting. And in this case with the faucet, we have the hot and the cold. They are very similar. And, the fact is in engineering design, you don't have to necessarily nail down exactly what sub-principle you're using. These are just approximate guides to help spur your brainstorming. It doesn't mean that you should be hung up on these subcategorizations. I mean, even between the major categorizations of separating in time and separating gradually, for example, we saw some overlapping concepts, and yeah, sometimes we would point out different nuances or different emphases, but the fact is you can also view a lot of these things as highly related and overlapping, and so it's a useful tool, it's a useful series of exercises to go through to help guide your brainstorming, but at the end of the day, what matters is the ideas that they generate for you and not whether you can properly identify or come up with the best classification for the particular brainstorming principle or separation principle that you used to get there. This is a means to an end, and once you use it to get to your ends, you don't need to be too concerned about how you describe the particular principles you used. So it's important to know it well enough to know how to go through it, but not to worry about how exactly you describe the details of your pathway. Now, having said all that, the different subcategories can be useful to help sort of steer our brains in different directions, and sometimes certain ways of phrasing a certain subconcept will click with somebody better than somebody else, and so it's all useful. There are slight nuance differences even between these items that appear to be very similar. For example, countering, as I was just talking about, tends to at least suggest that we're looking to completely negate something, to cancel it out. And whereas with coordination of parts, there may be some aspect that's being canceled out, but there's also a focus on keeping a constant output. And so in this example with the faucet, we're also concerned about making sure that the flow can stay constant, even if we're adjusting the extent to which the hot and cold are trading off. But at the proverbial end of the day, all of these principles and their various subcategorizations are only as good as their ability to help spur your brainstorming in as many different directions as possible, in a somewhat methodical way, just to help make sure that you've covered as much possible ground as you can. So the rest of the separation principles, we're going to go through more quickly, each of them, because we don't have as many examples, and it's not as often that you're resorting to these. They're further on down our hierarchy. So separation by direction is when something's property changes just by changing its orientation. So it has one property in one direction and a different property in a different direction, and sometimes by combining those facts you can get both of what you want. So you think through the various directions of opposing, right angles, rotary directions, and see if anything comes to mind. So going back to their old chestnut example, pile driving, we can see that if you were to drive it in on an angle, you get the benefit of its sharp tip while having the effect of a dull surface for purposes of vertical support. If you imagined joining several of them crosswise, then the net effect would be blunt support post-driving while still having it be sharp during the driving. Another example could be if you wanted to build a man-made pond in a subdivision neighborhood. You wanted it to be big so that lots of houses in the neighborhood could be near some water, have a view of the pond, but you don't want to have to spend as much on constructing it or maintaining it, and you want to conserve water. So having it be shallower is a form of separating in direction, as you're having it be smaller vertically, but still just as large horizontally. The next is separating by frame of reference. So the first aspect of this is by comparison. So they give the example of a situation where you're trying to make an actor appear to be taller, and so by using a shorter door frame or other parts of the set, you can potentially, to some extent, make him appear taller, although you'd have to actually coordinate that with a lot of other aspects of production, but in principle, that's possible. With separation by perspective, we're not actually changing the properties of the object. We're just changing how we're able to perceive the object, and that's sufficient. So you want to look at a bacterium. It comes too small to see with the naked eye. But you want to be able to look at it, so you don't need to actually enlarge the bacteria. It doesn't have to be small and large, it just has to be small and visible. So it's enough that it look large, and so a microscope allows us to alleviate that contradiction in separating by perspective. So the last two that we'll just briefly address deal with fields. Now remember, fields are not the core elements of our product. They're things in the environment or things that the product interacts with peripherally. And they may be very important to the operation of it, but they're just not they're not the core elements of our product itself. So here we've identified, say, field regions or fields that must respond differently. So then we want to find a material or a coating or a structure that changes the field response of the two regions sufficiently to resolve the contradiction. So the example they give is you have different conductive responses for a light bulb. You want a gas barrier that's conducting in order to illuminate the work area, and you want a gas barrier that's non-conducting in order to avoid UV radiation. So the response of the visible light to glass is conducting, and the response of ultraviolet light to glass is non-conducting. Separation between substance and field is basically for situations where the substance or element of interest has one property and the field that we're dealing with has the conflicting property. If none of the separation principles work, then the final thing to try is called compensation, and that's when you basically just address the concern that you have without regard for what else you might be making worse, and then try to compensate for that through some other way that doesn't directly relate to what you just did. I just want to say that these last 2 pages, from separating by direction onward, that we didn't have very many examples for, they're not very well developed in the book, especially these last 2 that deal with substances and fields. And so I wouldn't focus very much on them. I would focus much more on the first 6 of these 8 pages that we went through. And yep, let's see, that takes us through separation between parts and the whole. And I would not worry much about these last 2. Just know on a very high level that they exist and what general things they deal with, but that's about it for those. So hopefully this helps you to understand this summary of this ebook. It is useful. There is a lot of good content in there, and that's why I decided to make this screencast to talk through it and at least summarize the more important aspects in more detail, and in a way that I think is proportionate to their usefulness.